Okay, let's start day 2 of functions. Today we are going to look at inverse functions. So, take a look at these following diagrams. What do you notice about the two graphs, or even the two charts? Hopefully, you can notice that they are just the reverse of each other, meaning looking at the graph above, we see that our shoe size is our X and the foot size is the Y. But then we switch so that our foot size is the X and the shoe size is the Y. And in the two tables, that same process also happens. This is what we call inverse functions. An inverse function is a relation that results from exchanging the independent and dependent variables. So we're switching the domain and range, which, once again, remember your domain is your X values while your range is your Y values. So we're going to switch our X and our Y. Some new notation that you also need to know is that instead of using function notation, we have our inverse notation. So we say f of -1 of x for our inverse notation. When we solve for our inverse algebraically, we will then put this notation in front of the inverse to show it is in fact an inverse. Inverse and compositions. One way that we can tell that two functions are inverses is if we use compositions. We talked about that last time. So a composition is when you take one function and you plug it in to another function. So in the case of inverses, if we plug an inverse into its function, we should only get x left over. In other words, they're going to undo each other. So let's first start with an easier example and then we'll step it up a bit. So, given that f of x equals x plus 5 and g of x equals x minus 5 are inverses of each other, we need to verify this. So the first thing we're going to do is we're going to look at f of g of x. Hopefully you remember we're going to take g and plug it into f. So looking at f, we see our x right away. So we're going to go ahead and write down g, which is x minus 5. And then put our plus 5. So combine your like terms. We see that f of g of x is equal to x. So far, these two functions are in fact inverses. But it also needs to work the other way. So we need to now take g and plug f of x into it. So once again, f goes into g of x. Right away we see x again. So we go ahead and we say x plus 5, and then we put our minus 5. Well, we can see once again our 5's will cancel out, so we have g of f of x equals x. So yes, these are functions. All right, let's step it up a little bit. Let's verify that these two, f of x equals 2x squared minus 1, and g of x, which is equal to the square root of x plus 1 all over 2. So once again, we need to start with f of x, and we need to put g of x in it. Okay, so we put our 2. Now we have our x, so we have to put our parenthesis. We have the square root of x plus 1 over 2. square that, minus 1. Okay, so we got to do a little bit of thinking here. The opposite of squaring would be the square root. So if we are squaring a square root, those do cancel out, which means that we are left with 2 times x plus 1 over 2 minus 1. Then we have division and multiplication, so our 2's can cancel out. So we now have x plus 1 minus 1. So we see that f of g of x is equal to x. Okay, but remember, we got to do it the other way. So let's test that out. So we have g of f of x, and we're going to plug that in. So we have our square root, and oh, there's our x. So we got to plug in f of x. So we have 2x squared minus 1 plus 1 divided by 2. Now, with the division, let's look at it top to bottom. So on the top, what can we simplify? Well, hopefully you say the -1, +1. So we now have the square root of 2x squared over 2. Well, we see the 2's go away. So we have the square root of x squared. And what's the square root of x squared? You got it, it's x. So, are these functions? Yes. Oh, sorry, inverses. Yes, they are. Because when they were both composed together, they gave us x. Okay, so verifying is the easy part. But now we got to know a couple ways of how to find an inverse. Graphically, we can determine if something has an inverse. A function has an inverse if every horizontal line only intersects a function once. So this is like the opposite of the vertical line test. Okay, the vertical line test told us it was a function. The horizontal line test will tell us it has an inverse. And then a function and its inverse reflect over the line y equals x. We'll talk a little bit more about that one in class. Here are the 6 steps to how to find an inverse algebraically. Remember, if you need to pause and write them down, you can. The first thing we're going to do is determine if the function has an inverse by using the horizontal line test. We're then going to replace our f of x with a y. Because an inverse is switching the x and the y, we got to switch our x and y. We're then going to solve for y. And once we've done all of that, we can put in f of -1 of x in for our y. And step 6, I won't be too picky on, but if you want to double check your work, always verify. So let's find this inverse algebraically. Well, first thing you can do, you could type it in your calculator to discover that indeed it will have an inverse. The square root function, which we will look at more coming up, looks something like this. So a horizontal line is only going to cross through it one time. So we're good on going ahead and finding the inverse. So our first step is complete. Next, we want to replace our f of x with y. So we have y equals 3 times the square root of x minus 1. Now we switch x and y. So x equals 3 square root of y minus 1. Okay, we got to isolate that square root. So we got to get rid of the 3. So we divide. So we have x over 3 equals the square root of y minus 1. So we talked about earlier A square undoes a square root, so we got to square both sides. Now this is the thing you have to remember. We have now put parentheses around this x over 3, which means nothing else can change inside the parentheses, only on the outside. Now I'm going to rearrange this so that it's y minus 1, because we're used to seeing y come first. So now to get y by itself, we add 1. And remember, it can't go in the parentheses, so we have y equals x over 3 squared plus 1. Well, we've done all the work, so now we go ahead and we put our f of negative 1 of x equals x over 3 squared plus 1. And once again, on your own, you can verify that these are, in fact, inverses by composing them together. All right, probably should have done this one first. It's a little bit easier. First step we need to do, make this into y equals 4x plus 2. Switch our x and y. And now solve for y. Now, when we get to this point, we're going to split this up. So we have x over 4 minus 2 over 4. And we're going to reduce where necessary. I would really like to not see decimals. So I'm going to put this into one step here, because we know we found the inverse. So we have our inverse notation equals x over 4 minus 1/2. All right, we got one more example here real quick. F of x equals 1/2 x minus 3. So we replace this with y equals, switch our x and y, and solve. So we first want to add 3 to both sides. I'm going to go ahead and put my y on our left-hand side. All right, and think of this like division. We need to get rid of 2. So we got to multiply both sides by 2. Now, notice I put parentheses around our x plus 3. We need to distribute this 2 in, because we're multiplying both things on that side by 2. And then finally, inverse notation. All right, well, I hope you have a little bit better understanding of inverses. Just remember that an inverse from a function is switching the domain and the range of that function. We are then just solving for y, and it always needs to pass the horizontal line test first.